All right, so we're still continuing on with kind of our circuit analysis. So, a couple times ago, we looked at very simple circuits. We had a voltage source, we had a current carrying wire, and we had a resistor that resisted that flow. Essentially, that's what allows us to take electricity and do work with it, whether it's, lighting up a light bulb, powering an electric motor, that's our resistor. Last time we looked at, well, what happens if we put more than one resistor in a line on the same wire? So we said that the resistors were in series. That was a series circuit. Today, we're going to look at what do we do if instead of it all being in one loop, what if our resistors each had their own loop the electricity could go through? So I still have a voltage source, and we've got three different resistors on it. Um, but now my electricity, like if I'm looking at an electron going from negative to positive, or the electricity flowing in the opposite direction, my electricity has a choice. It can either go through the first resistor, it could either go through that second one, or it has a choice to go through the third one. I continually have electricities flowing out, electricities flowing this way. Um, and so there's going to be electricity flowing all three, but there's going to be differences between that current, okay? So remember with series circuit, what we said was I was always the same for all resistors. Essentially what we're going to see is for parallel circuits, the voltage is the same for all resistors. Because keep in mind, for circuit analysis, everything needs to essentially kind of come back to I equals V over R, or V equals I times R is equal to V over I, okay? Everything's going to boil down to Ohm's law at some point here, all right? So for parallel circuits, what we know is that the voltage is the same for all of the resistors. And that kind of makes sense. Like there's a wire going from here through there to there. There's a wire essentially connecting all three of these, but the voltages are going to be the same. So now the question is going to be, first off, how do I solve for current? Or how do I solve for resistance here? How do I figure out the total, or even what's the total voltage here? How do I apply Ohm's law here? So for series circuits, we said the equivalent resistance was equal to R1 plus R2 plus, we just added the resistors together. Parallel circuits are going to be a little bit different. The equivalent resistance is going to be equal to 1 over R1 plus 1 over R2, or kind of the inverses, plus 1 over R3, plus, you just continue that for however many resistors you have in parallel this time, okay? Because when you diagram them out, these resistors are in parallel. That's where, I should probably name that. That's where a parallel circuit gets its name, is these things are diagrammed out. They're parallel to each other. Oh, other thing here, so it's not just that. Essentially, once you get done adding up the inverses of all those things, you have to then take it to -1 to get it back. The way that it used to be kind of explained was 1 over the equivalence is equal to 1 over R1 plus 1 over R2 plus, okay. So this is the way it used to be. I kind of like it this way because it actually tells you the math that you have, the final step you have to do to solve for the equivalent resistance, all right? So let's actually look at a parallel circuit here. So let's say, you know what, I'm going to go back to my 12-volt battery. How do I want to do this? We'll go like that. And we're going to go with a 2 ohm resistor, a 3 ohm, and a 4 ohm resistor. All right. And I kind of just want to know what's my total current going through here. Okay. So I total will be equal to voltage over equivalent resistance. Okay. So my voltage is going to be the same for all of these. All right. The voltage is the same. That is the key to analyzing parallel circuits. All right. So to figure this out, my equivalent resistance is equal to, so my 3 resistors here I have, and we're going to say that this one's R1, this one's R2, and that one's R3. All right. So R1 is 2 ohms, so I've got 1 over 2 ohms plus 1 over 3 ohms plus 1 over 4 ohms. But then, in order to kind of get this right, I'm going to take the inverse of that. So let me go ahead and get out a calculator quick, put it in place where I can see what I'm doing. So I'm going to go parentheses, parentheses, because I got a big parentheses, but I'm going to do each fraction as their own parentheses. 1 divided by 2, closing parentheses, plus parentheses 1 divided by 3, close parentheses, plus open parentheses 1 divided by 4, close parentheses, close parentheses, okay, but I'm not done yet. I'm going to raise that to the -1 power, and I get a total current of 0.923. Yeah, I'm going to call that good. So 0.923 amps. So not quite. Actually, let's just call that 0.9 amps, just to make it a little bit easier, okay? So that's the equivalent resistance for this circuit. So really, I can treat this like it's a simple circuit where, oh, that was dumb me. That's not amps. Oh, nope, let's go back. That's voltage. That was silly of me. Resistance, ohms. I'll get it right eventually. Or 0.9 ohms, okay? So now I've got a resistance that I can put into Ohm's law, I equals V over R. All right, right there. So now I've got, so if I wanted to solve for the current, total current, voltage we said was 12 volts. The total current we have going through all these things is 0.9. That's a 0.9 ohms. This number is going to be just a little bit bigger than 12. 12 divided by 0.9. 13.3 is where I'm going to leave it. All right, so 13.3 amps. All right. So total current I have going on here is 13.3 amps. Voltage is the same for each of these resistors. So just like with the series circuits, where the current was the same through all resistors and we had voltage drop off for each resistor, what we're going to see here is we're going to have a current. The currents will be different through each resistor. And that makes sense. You know, most of your electrons are going to go through where there's least resistance. So if I come back to Ohm's law, if I want to figure out how do I find the different current through each one, like if I want to know the current going through resistor 1, I'm just going to take the voltage and divide it by resistor 1. Or if I wanted to kind of generalize it, the current going through whatever resistor I'm talking about, let's call this parallel current. Okay, whatever resistor I'm talking about that I want to know the current for is going to be equal to the voltage, which is the same for all of them, divided by whatever the resistance is for the resistor I'm talking about. So this will be kind of the second big takeaway. All right, so we've got one big takeaway there. That's kind of the second big takeaway. This is the third thing that you're going to want to have written down. All right, so let's actually figure out what's the current going through these things. I'm going to work over here. So if I want to know the current going through resistor 1, it's just a voltage over resistance 1. If I want to know the current going through number 2, voltage over resistance 2. Current going through 3, voltage over resistance 3, right? I'm repeating it 3 times because I've got 3 resistors. Luckily, all of the resistors are 12 volts. All right, resistor 1 we said was a 2 ohm resistor. So we've got 12 volts divided by 2 ohms. If I remember right, it should be 6 amps. Okay. So I've got 6 amps of current kind of going through the small loop here. Okay. For the second resistor, I've got 12 volts divided by 3 ohms. And that should give me 12 divided by 3 should be 4 amps. Okay, we're doing good so far. Uh, so there's slightly less current going through that one. And for the current through that third one, so I've got 12 volts again, but this one's going through 4 ohms. And this should get me 3 amps there. Okay. So my total current looking at, so now if I kind of look at my current total here, 6 plus 4 is 10, plus 3 is 13 amps, you know, if I kind of forget the 0.3 there, these are pretty much equal, okay? And just remember, this difference came from the fact that this was like 0.9 to something, you know, which is, I just rounded it off, okay? So this guy cut through my work there, and this guy should be, you know, about the same. I'm 0.3 off because I just rounded very poorly. But yeah, so parallel circuits, they're still pretty easy. You know, everything's still boiling down to I equals V over R. But in this case, solving for your equivalent resistance, that gets to be a little bit tougher just because we're working with the inverse of it. But that's parallel circuits. That should be enough to get you guys started. Good luck.